All right, well, good morning, everyone. This is intimidatingly great, if that's such a thing. So welcome all, and thank you very much for attending this conference and for the talk. And before I start with this talk, I just want you to give a round of applause to the organizers, because you're all here in person, and that's a great thing. Now, how many of you have been affected by the pandemic, sitting at home, not being able to go anywhere? Great. So in light of this, and because I'm a coach, we will do a little bit of a physical exercise. So please stand up for a second. This is going to be awesome, I promise you. Look, you had 1 year to sit and rest, so it's going to be cool. Okay, so here's what you need to do. Raise up your arms like that, elbow to the head, like that kind of, yeah, okay, good. And now, start clapping. Clap, clap, clap. Thank you. So I did this here 2 years ago. Who saw that 2 years ago? Fooled you again. Okay, so welcome. I'm here to talk to you about WebAssembly and JavaScript. So what we're going to talk about today goes back to 2018, where this is an overly simplified view of the web platform. So you have your browser. Inside the browser, you have this magical thing that takes your JavaScript code, and it's able to compile it, interpret it, and essentially run it. So there's this virtual machine that is able to understand and work with your JavaScript code. Okay? This is a very simplistic view, but remember, this is how the web platform, this is how browsers used to look 2, 3, 4 years ago. And so there's no denying the fact that today, the web is growing at an incredible rate, right? So even if you compare applications that you saw or you developed 5 years ago or 10 years ago with what you are doing today, there's an awful difference, right? There's more JavaScript frameworks, there's more technologies, there's more stuff that you can use, also websites that you visit, there's animations, there's all sorts of great stuff happening. And we do use JavaScript most of the time, and that's great, but JavaScript has certain limitations, right? There's always things that you can do, lower level things that are going to be great, but it may come at a cost. So essentially we try to push, or we are pushing JavaScript to its limits, or I should say we are pushing a language that was intended to do something else to its limits, and we're pushing it outside its comfort zone. Now, you can do amazing things with JavaScript, right? You can do low-level processing, you can do calculations with JavaScript, but sometimes these things will introduce performance impacts. Now, I have a little note on this slide that says, the V8 and other JavaScript compilers sometimes even help you to create performant JavaScript, but they also have some limits, right? So essentially, you have to be very careful on how you write your JavaScript, how you call your functions, etc. There's a lot of science that goes behind it, and then these compilers will also allow you to write, or they help you to create more performant code, but they also have their limits, right? So you're going to hit a limit in some edge cases where JavaScript is just not going to be good enough. So of course, there must be a better way where you can create applications that perform well on the web, that allows you to execute code really, really fast, and they allow you to do lower level processing of certain things. And this is when we have to say hello to WebAssembly. Okay, so WebAssembly has a little bit of a history. So some of you may be familiar with a thing called asm.js, which got developed, I think, by the Mozilla Labs back in 2013. And this is really the beginning of this whole WebAssembly journey. So asm.js, very simply put, allowed you to take applications written in C and execute those on the web. And this is essentially what WebAssembly allows us to do. And you see this history. So there's 2015, WebAssembly was first announced. 2017, an MVP product was created. But what is really important is that in 2019, WebAssembly became an official W3C recommendation. So that means that on top of HTML, CSS, and JavaScript, WebAssembly is also part of the web ecosystem. So it's as official as it gets. So what is WebAssembly? So if you go to MDN, you will find a paragraph which I really, really like, and it's a really good explanation of what WebAssembly is, and it tells you that it's a low-level bytecode, yada, yada, yada. I could have copied it, but I think it's overly complicated, so I created my own very simple explanation, which is essentially, it takes code that is written in a non-web-based language, and it allows you to execute that code in a web-based environment. So what does that mean? That means you have some C++ code, you take that, you compile that to WebAssembly, you take that WebAssembly module, you add it to your browser, and now you can run that code at a native speed. So what does that mean? It means that you can run and execute that code as fast as you would execute that in your CLI, the binary version of that code. Okay, so that's my very simple explanation. Now, oftentimes, I hear people say, well, you know, is WebAssembly going to overtake JavaScript, or is it going to be the new JavaScript? Is it going to be as popular as JavaScript, et cetera, et cetera? And what's really important to understand here is that WebAssembly and JavaScript complement each other, right? So WebAssembly helps JavaScript become better. And it does that by this API called the WebAssembly JavaScript API, which is part of the web APIs. So we have, you know, fetch and some Bluetooth APIs and, you know, a bazillion other APIs for the web APIs, and the WebAssembly JavaScript API is one of those as well. This WebAssembly JavaScript API allows you to essentially work with the WebAssembly modules that you create, right? So you have this WebAssembly module, you can load them, you can call functions from this WebAssembly module, and that's why I'm saying that JavaScript and WebAssembly complement each other. They are not competition. There's, you know, there's no, hey, WebAssembly is going to be much better. Both of them are good, and they do complement each other. So what this WebAssembly JavaScript API allows you to do is to use the power of WebAssembly, which I'm going to talk to you in just a minute, and then at the same time use the flexibility and use all the cool stuff that we use in JavaScript. So basically you use the best from both worlds. So how do you create WebAssembly modules, or how do you work with WebAssembly? And I'm going to show you a very simple example, and before you tell me, yes, I know you can square numbers in JavaScript, thank you very much, I'm very well aware of that, but this is just a simple example to show you how to take code, in this case written in C, create a WebAssembly module, and then consume that in a web application. So very simple code written in C. You also see this thing called mscripten on top. Mscripten is a separate tool that you need to install on your machine. It's very easy to install. You go to mscripten, I think, .com or something. There's some couple of instructions, and it will install a compiler for you. So you write some code in C. The next thing is that you run the emcc, which is the mscripten compiler. And here what we are saying is that please take that square.c file, create a WebAssembly module. So you set wasm to equal to be 1. So you want to create a WebAssembly module. And then there are some additional options, which I will mention in just a moment. And then also notice that .o square.js. So if you run this command, you're going to end up having two files. One is going to be square.wasm, which is going to be a WebAssembly module. And then the other one is going to be square.js. This JavaScript file is referred to as a glue code. This JavaScript file is something that you will need to add to your HTML, and this will allow you to call the functions that you expose from C via your WebAssembly module. So it's basically a connector between your HTML, your JavaScript, and the WebAssembly module. And that is created to you automatically if you run this emcc command. Then you load WebAssembly using JavaScript. And what's really important is that you also need to load the glue code itself. So you need to add that square.js to your HTML, and you do that via script tag, for example. And once you do that, you will have access to this module object. And what I'm doing here, the first 4 or 5 lines are essentially, I'm creating an API object where I have a calculate square property, and that calculate square property calls module.crap. So module.crap was something that I exported via the emcc command, which is basically wrapping my C command into a JavaScript object. So very simply put, what that means is that later on in my code, if I call api.calculateSquare, and if I pass in a number, which in fact I'm doing in the last line, it is going to invoke that C function. So I'm effectively squaring the number via WebAssembly via C, okay? This is a very simple example, but hopefully it shows you that WebAssembly is not this magical thing that you need to be afraid of. It's in fact very, very easy to get started with it. Now, this is a very trivial example because, as I said, you can square numbers in JavaScript. Why would you want to do this? Still, it's good for demonstration purposes. And then what is the next step is that you just run your web app, right? So you have your HTML, you build up your entire web application, and then you get on with your life. Always use the glue code. This is just a reminder, because sometimes I forget to edit, and then I don't have access to that module object, and then I get all these weird errors, and then I realize that I forgot to add the JavaScript code that mscript then provided. Now, a side note. So C, C++, and some other languages are considered LLVM languages, right? There are some other languages that also have a compilation target to WebAssembly. So one example is Go. And there's a GitHub repository, I think, which I'm linking to in the resources. And this person collected all the languages that have a compilation target to WebAssembly. But Go is slightly different. So in terms of Go, you write your Go application, and then you use the Go compiler to compile that application to a WebAssembly module. And if you do that, it's not going to produce a glue code for you, but you can get the glue code from the Go, I think it's a GitHub, or from the documentation. It's called exec_wasm. And that is the file that you need to add to your HTML. The other difference with Go and the C or C++-based WebAssembly module is that from Go, you can do very, very interesting things. In fact, I would probably recommend you to start with Go, because if you create a Go application, believe it or not, you can do things like document.getElementById from your Go file. So you can directly access your DOM from within the context of your Go application, which I think is very, very powerful, and it's an easy way to get started with WebAssembly. So, all that being said, why would you want to use WebAssembly? There are a couple of sort of use cases, and one is you want to reuse existing code. So you have a C application, you have a C++ library or a project, or you have something in Go, and now you want to run that on the web. So you basically take that code, compile it to a WebAssembly module, and now you can utilize that on the web. That's basically one of the use cases. The other one is predictable performance, and what I want to highlight here is the term predictable. So if you write JavaScript, because JavaScript is weakly typed, it's not strongly typed, so you don't have the data types, there's a lot of stuff where performance can change based on how you're using the application. Whereas with WebAssembly, because it's strongly typed and because there are some other properties that it has, the performance is always going to be the same. Because what you're going to provide the browser and this engine that the browser has is going to be always the same, right? Because you have to build this ahead of time. So you get this predictable performance. Binary size is another thing. So there was some research done where, I think it was from Google, where, excuse me, they basically created the same code using JavaScript and using WebAssembly, and in some cases, the WebAssembly module was significantly smaller. And if you want to do some advanced stuff, so things like threads, SIM-ID, shared memory, then of course you have to use WebAssembly because JavaScript just cannot do that. So the web platform today, so the only change is that you still have this virtual machine that is still able to compile and interpret your JavaScript, but the same virtual machine, so it's not an addition in the browser, it's the same engine is also able and capable to work with WebAssembly modules. Okay, so this is how the web platform looks like today. This is part of most, I think actually all modern browsers. So you can run this in Safari, Firefox, IE, so on and so forth. Time for the demo. How much time do I have left? I have 15 minutes left. Okay, cool. So I'm going to show you two demos, right? And one is going to be use case number one that I talked about. By the way, is this large enough? Can you read that? Okay, perfect. So before I do this, let me show you an example. So I work for a company called Cloudinary, where we basically allow you, who knows Cloudinary, by the way? Yes, my people. Okay, so what we do is we allow you to store your media assets in the cloud, and then we give you this access URL, which you see in the address bar. If I zoom in, then you will see it. So that's the address bar, and that is the access URL for this, in this case, in this image. If you upload a video, you get an access URL for a video, etc., etc. So this is what I would call the raw asset, right? So someone upload this image, I am now requesting this image, and this image is 1.4 megabytes in size, right? And that's great. Now what Cloudinary allows me to do is to, if I zoom in here, is to add something like an f-auto and a q_auto, which is going to basically, so f-auto is short for automatic formatting, which takes the browser into consideration. It says, okay, if you're using Chrome, then I'm going to render a WebP image for you automatically, because WebP is the most optimal image format for Chrome. However, if you open the same URL in a browser that does not support WebP, for example, a Safari, it is going to generate maybe a JPEG 2000 for that particular browser. And then Q-Auto is going to automatically reduce the quality of the image in a way that it's not affecting the human eye. Okay, so I don't know how much you can see that, but it's not pixelated. It's the quality of the image is the same as it was before, seemingly. However, adding these two flags means that we went from 1.4 megabytes to 853 kilobytes, right? So I saved a lot of bandwidth just by doing these two things. And if I check the headers, well, this is a JPEG, but let's shrink this down to width 500. And then hopefully this is going to show that this is a WebP. Okay, so now we change the format as well, right? So a smaller size means that a WebP format is more applicable. But basically, Cloudinary figures this out behind the scenes. So I don't need to know if a width 500 image should be a WebP or a JPEG. All of that is done automatically. So why am I telling you this? Well, because we have two projects that are using WebAssembly that I want to showcase to you now. And the first one is this thing called Simulacra. Simulacra was created by one of my colleagues in 2017, a guy called Jon, who's an image researcher at Cloudinary. And Simulacra is structural similarity unveiling local and compression-related artifacts. You all know what it is now, so I can move on. No, I didn't know what it was, but essentially, think about it this way. You have two images. You have one image, and you have those images in two different qualities, right? You have a full-blown quality, and you have a reduced quality. The Simulacra project, this C++ file that you see here, is capable of telling if those two images are similar or not. In other words, if one image is heavily pixelated, or more pixelated than the original, it's going to tell you, well, there are some visual artifacts and defects in this image, so I'm not going to tell you that these are not really the same. And there are some projects, and you can read all this research by Philip and some other people, but essentially how this Simulacra project by Jon is different is that it takes user information into consideration as well. So Cloudinary has done a lot of research into showing actual people, actual images, and we ask people, here's image, here's a quality reducted image, can you see a difference? Yes, no. Okay, and we basically collected all that information, and then essentially there was this big research, and you see this C++ file was created. Now, the problem with this C++, well, it's not really a problem, but how this C++ project was created a couple of years ago was that I need to create a binary, and I can run it on my CLI. Parameter 1 is image number 1, parameter 2 is image number 2. And then comes Tamas and says, why don't we run this on the web? And this is when my 6-month project, no, I'm kidding. This is when my 2-week project started. So essentially, I tried to port this application to the web. Now, I did write a blog post about this, so if you're interested, you can read that. But ultimately, I used mscripton, and I took this C++ project, and I ported it to the web using WebAssembly. So you see there are two files here, simulacra.js and simulacra.wasm. These are the two outputs that I got from running the mscripton compiler, so EMCC, the same stuff that I showed you using square.js. The one thing that's really interesting here is that what I do is I basically use a front end, which I'm going to show you in just a moment, where you can enter two images, or you could either upload those two images, but in this case, I'm using two Cloudinary URLs, and I basically take those images and write them to this virtual file system. This virtual file system is part of that virtual machine that I said, and it has access, or WebAssembly has access to this. So WebAssembly module.fs file system.write file, you can directly write files into this virtual file system. So I write two of these files, and then I call the calculation method from this Simulacra project. I can do this because I ported that C++ project to a WebAssembly module. So what happens now? Nope. So this is the front end that I built for it. So you have this first image, you have this second image, and I have this flag, which is q_1. That flag is going to produce a quality 1 version of that image. So you will actually see that it's going to be a very, very low quality image. So if I expect this simulacra tool to tell me that you should not show this to people because they're going to notice that this is an optimized image, which I'm sure you do notice this is an optimized image, right? And so the way this tool works is that it's going to calculate a score, and if that score is above 0.1, those two images are not the same because there are some visual defects in the image that should not be shown, right? So this is clearly showing 0.4. So if I do quality 100, it should tell me that this is 0 because I'm looking at exactly the same images. And how we use this is when we say QAuto. So if we say QAuto, I said we automatically reduce the quality of these images, and so we want to make sure that the image, that it gets automatically quality reducted, is not different. So 0.03 is well below 0.1, so we can safely say that these two images are the same, okay? So that's one way how I basically ported something that was written in C++ to the web. Now the other example that I have is related to this sort of FAuto, this automatic format selection thing that I showed you. So I built this tool using Go, and I'm going to show you the Go interface in just a moment. But basically, I allow you to have, in this case, it's a Cloudinary URL because I prefixed the URL with res.cloudinary.com. It could be any image on the web. And I have this FAuto flag in here, and this is a JPEG. And I have the user agent set to be this is, should be Chrome, unless, I found a way to override the user agent, by the way, using the DevTools, but I think this is, no. Now we are Chrome. Okay, so this is now using Chrome. So if I hit check, I will get some information back from the image, right? And I get, okay, so this is a JPEG, it's around quality 88, there's the dimensions. But what if I now go and say width 500, remember that was a WebP image. Now, even though the Chrome DevTools will tell you that, yes, the header is image WebP, what if you want to go one level deeper? What if you want to further analyze that image? What kind of WebP it is? Is it a VP8 container? Is it a VP8L container? There's lots of image container stuff that I could go on. And so this tool allows me to do exactly that, right? So now I'm not only saying that, hey, yes, this is a WebP, I'm saying this is a WebP image, which is a VP8 container, and it's a lossy one, and it doesn't have any alpha channels. Now, doing this extra analysis is only possible because of the Go code that I created, and then I ported that Go code to WebAssembly. And the way that looks like is right here. So I have...
Get that. Could you try again?
Yes, I may certainly try that again. Sorry about that. So, I have a separate Go file for checking JPEGs, checking PNGs, checking WebPs, etc. But what this allows me to do is to do some low-level, I'm not going to go through the code, of course, but it allows me to do some very low-level processing of the image data, right? So maybe I will show you PNG because that's sort of easier to understand, right? So I say, okay, if, I don't know, byte number 24 is 0, then the PNG is grayscale. If it's 2, it's true color. So I can analyze the PNG images that I have at a very low level. And I also said that Go works differently. Notice that in my main Go, I have this thing, document, get element by ID, response tag, stat inner HTML. So basically from my Go code, which I will then compile to WebAssembly, I can very, very easily access the document object model, okay? And I can set an inner HTML for a particular element. And what I do here is just, I basically prepare the text that I want to output. If this is a WebP, I say if it's lossy, I say lossy, if it's lossy, it's lossy, etc. And then I construct that message and I just print that into the DOM from this Go module. The way I created the WebAssembly file was just running this command, which is the Go build command, setting the architecture to be WebAssembly module, right? So I tell the Go compiler to prepare a WebAssembly module, which then creates a WASM file for me. I needed to download this wasm_exec.js, which I mentioned is the glue code for Go applications, add everything into my HTML, and that's pretty much it. So when I essentially click that check button, I just invoke I invoke that Go method. Okay, slightly different functionality, but still allows me to do a lot of lower level stuff. Okay. So I'm going to leave you with a bunch of resources. There are some really, really good examples out there today that use WebAssembly. One that you may have heard about is the Squoosh app, which is an app from Google, which allows you to do image optimization in the browser, just using front-end, so they don't use any back-end code. And what they do as well, sometimes they use JavaScript to use the built-in JPEG encoder to reduce the quality and optimize JPEG images, but they have a selector where you can use other JPEG libraries, and those are via WebAssembly. Okay, so they run those through via various WebAssembly commands. Someone did port, Doom, the classic game, and Super Mario using WebAssembly to the web, so you can run games. There are, many, many good examples. And then the last link here is that simulacra port. So if you're interested how I, went through this process of bringing that simulacra CPP file to the web, I basically created that blog post so you can read all about that. Okay, that was me. Danke, merci, grazie. Thank you very much for your attention. And I think we have questions. Thank you.
Thank you. What do you feel now?
Good.
Yeah, good?
Yeah.
All right. Then questions. Again, please go to slido.com, put in the code, or raise your hand if you want to. I'm going to try and scan the room. So we have a couple of questions, start with, what's the performance like on cheap mobile devices? We've gotten to know a couple of ones in the talk before, if you remember, like a Redmi or whatever that Russian device was.
Russian device. Okay. So what is the performance?
What's the performance
What's
like?
the performance like
Yeah.
on? I don't know. That's a good question. So the reason why I don't know is because I never tested this on a Russian mobile device. I'm sorry, I don't know.
Try it out, and then you'll know. Okay, next question. This one comes from Martin. Is there a use case for WebAssembly to be used in a Node.js environment?
I think I've seen something where, what was that? There was, maybe it was Deno, or Deno, I don't know how to pronounce that. So I've seen something where people were using WebAssembly. I don't know if there's a particular use case for this, but I'm just trying to remember. So don't quote me on this, but I think there was, Deno, that new Node.js, essentially. So Deno has a module, I think, which allows you to work with WebAssembly. So in that sense, I'm sure you can do that, but I don't have particular use cases.
What if I rephrase that question into, is there a good use case for WebAssembly?
Yeah, okay. So use cases for WebAssembly, as I said, lower level processing tasks. So with the addition, so there's this new spec with the SIMD, which is, single, not input, single instruction, multiple data. Yeah. So essentially, these type of operations are very, very good for audio codecs, image processing, video processing. So if you have computing heavy tasks, then it will always be a good choice to use WebAssembly, right? Because JavaScript has this single thread, etc., whereas with a WebAssembly module, you get multi-threads, you get SMD, SIMID, sorry. These are all things that will help with achieving lower level tasks in a much performant way. And so if you can use this from a Node.js, a Deno, etc., then that is going to help.
Makes a lot of sense. Thank you. Okay, so many new questions. All right, why should you access the DOM from WebAssembly? Shouldn't we treat and use the WebAssembly as an API?
You should. So the reason why I showed you that is because that's the Go implementation. That's how the people who created Go decided to do that. I didn't do it, but so that's what I'm saying. You know, if you have C, C++, Rust, etc., all these languages, then yes, you would have to use the WebAssembly JavaScript API to stream that WebAssembly module into your application, and then create these API object where you call the methods, etc. The Go implementation is, I'm going to say, fundamentally different from this, but I wanted you to see that as well. So it's just one way to implement it. This is not necessarily the right way. Ask the Go people why they did it. I'm also going to say that exec_wasm JavaScript file that the Go developer community provides, it actually brings a sort of simplified Go runtime environment into your browser. So it's going to be maybe a large-ish file, okay? But still, that's how they decided to do that.
Cool. So again, ask someone else. All right, this question is coming from Matthias. Is there a way to use WASM for WebGL performance enhancement? Good question.
I never use WebGL, I'm so sorry. Matthias, I don't know where you are. I'm terribly sorry, so I don't know. I guess, no, I'm not going to guess.
Would you like me to ask you a question that you can answer?
Is that a trick question now?
I don't know.
Okay.
Is there a question that you get a lot that you just like to answer now?
I get two questions that actually one is the PWA thing. Can you use WebAssembly in a progressive web app? Can you use WebAssembly in an offline application? And yes, you can. Because the WebAssembly module is the same, it's just an additional resource that you can cache, just like how you would cache a JavaScript, a CSS file. And in fact, the Squoosh application that I showed you, or not showed you, sorry, told you about, from Google, I think that's a PWA as well. So when you install that and you go offline, you will see that you can still, use even the bits and parts that reference WebAssembly.
Cool, thanks. All right, let's try this question.
Okay.
Could you theoretically build an operating system with WebAssembly?
What? I'm going back to virtual events. No, I'm kidding. I will quote Tamas from 2 minutes ago. I don't know. I'm sorry. I never tried. Is there a name? It's not that I'm going to find. I'm just.
It's Anonymous.
It's Anonymous. So Mr. Anonymous. So
California.
Miss Anonymous. Try. And see you next year here, and then you can tell me.
Yeah, give a talk on that if you ever do that.
Yes.
And also build the operating system on like a README maybe, then we have like 2 questions answered. That would be great. Do we have any questions here maybe? Anyone want to? No? All right. Okay, there's one more question here.
I don't know.
Good luck.
All right.
Using the F-auto transformation is very cool. I sometimes had issues with videos becoming super bright on Windows. Any advice to ensure this does not happen? I feel like you should pay a consulting fee now.
Yeah, 50 Swiss francs. No, I can answer this, thank God. Yes. So F-auto, you can use F-auto for images and videos, right? So I don't quite understand, was it bright?
Yeah, videos becoming super bright on Windows.
Okay, I don't know why that's the case, but I can tell you that if you upload a video to Cloudinary and you add an F-auto in as part of the URL, then if you open that link in Chrome, it's going to be a WebM. If you open the same link in Safari, it's going to be an MP4. Brightness, I don't know.
Turn down your display brightness, probably.
Yeah.
All right, that was the last question. If there are no questions from the floor, then, guten Appetit at lunch, and see you in about an hour with web cartography unfolded. So, see you later.
Right, thank you.